Welcome to The Explainer. Okay, today we are tackling a pretty huge topic, our picture of the universe itself. And wow, how that picture has changed over time. We're going to be drawing from the incredible work of Stephen Hawking to trace this amazing quest humanity's been on, to figure out the cosmos. We'll go from ancient myths right up to the very edge of what we know today in physics. So let's get started on this journey through space and time.
To really get a feel for how far we've come, you gotta hear this one famous story. So, picture this. A well-known scientist. He's up on stage giving a lecture about astronomy. He's explaining how the Earth goes around the sun and how our sun circles the center of our galaxy. The whole deal. Well, when he's done, this elderly woman in the back stands up and says, "Everything you just told us is total rubbish. The world is actually a flat plate and it's sitting on the back of a giant tortoise." The scientist, he kind of smirks and he asks her, "Okay, and what's the tortoise standing on?" And she just fires back, "You're very clever, young man, but it's turtles all the way down."
Okay, so an infinite stack of turtles. Yeah, that sounds pretty absurd just now, right? But that story, it actually gets at a really fundamental point. We humans, we've always needed some kind of model, some picture in our heads, to make sense of the universe. And to finally move past the myths and the turtles, well, humanity was going to need a brand new, super powerful tool. And that tool was scientific observation.
So one of the first huge leaps forward came way back around 340 BC. The Greek philosopher Aristotle noticed something so simple but so profound, just by watching ships out on the horizon. See, he thought if the Earth were flat, a ship would just show up as a tiny dot that gets bigger and bigger. But that's not what he saw. No, what actually happens is you see the sails pop up first, then you see the hull of the ship. And Aristotle realized, wait a minute, that can only happen if the ship is actually coming up and over a curved surface.
I mean, that's the power of observation right there in action. And get this, Aristotle had another piece of evidence that was maybe even more clever. He looked at lunar eclipses, when the Earth gets between the sun and the moon and casts a shadow, and he saw that the shadow on the moon was always a perfect circle. Now think about it. If the Earth was just a flat disk, its shadow would usually be a long, stretched-out oval, right? It would only be a circle if the eclipse happened at the exact perfect angle. The fact that it's always round, that was basically undeniable proof. We live on a sphere.
So this idea of a spherical Earth led to what we call the Ptolemaic system, and it put the Earth right at the center of everything, with the sun, moon, and planets all carried on these nested crystal spheres. And this model was so convincing, it completely dominated Western thinking for over 1,500 years. Just think about that. Then, in 1514, a guy named Nicholas Copernicus comes along and suggests something totally radical. He says, hey, what if the sun is at the center? And that idea, well, it started a revolution that would quite literally move the Earth. But here's the thing. The Copernican model, as good as it was still missing a really crucial piece of the puzzle. It was great at describing what the planets were doing, orbiting the sun, but it couldn't explain why. Why were they moving like that? Well, the next giant leap forward came from the mind of Sir Isaac Newton. He was the one who finally figured out the engine, the mechanism that makes the whole system tick.
So, in 1687, Newton publishes this work that you could argue is the single most important book in the history of physics, seriously. And in it, he lays out his law of universal gravitation. And that word, universal, that's the absolute key, because for the very first time, a single elegant law explained why an apple falls from a tree on Earth and why the moon stays in orbit around the Earth. The rules up in the heavens were the same as the rules down here. They were one and the same.
And just like that, our entire picture of the universe changed. It wasn't this place of, divine mystery and unpredictable gods anymore. Instead, the cosmos seemed like a giant, perfect machine, a clockwork universe. And if it's a machine, that means its every move could be calculated and predicted, as long as you knew where everything started. It was orderly. It was knowable.
And for more than 200 years, this idea of Newton's clockwork universe was it. It reigned supreme. His laws seemed to explain literally everything, and with stunning precision. But then, right at the dawn of the 20th century, a really strange discovery about light itself threatened to just shatter this beautiful, perfect machine.
So here was the problem. A bunch of super precise experiments, famously by two guys named Michelson and Morley back in 1887, they found something that just seemed impossible. They discovered that the speed of light is always constant. It doesn't matter if you're flying toward a beam of light or speeding away from it. When you measure its speed, you get the exact same number every single time. And that one simple fact just completely breaks Newton's laws.
It breaks all of our common sense, really.
This train example really nails the paradox. So, according to Newton, speeds just add up. Simple. If you're on a train going 90 miles an hour and you throw a baseball forward at 10 miles an hour, somebody on the ground sees that ball flying at 100 miles an hour. 90 plus 10. Makes perfect sense, right? Okay. But if you turn on a flashlight on that same train, both you on the train and the person on the ground measure the speed of that light as being the exact same. How is that possible? I mean, how could this be? It was a full-blown crisis for physics.
The solution finally came in 1905, and it didn't come from some famous professor at a big university. No, it came from a young patent clerk working in Switzerland. His name was Albert Einstein, and he proposed a solution that was so radical, so mind-bending. It meant we had to throw out ideas we'd taken for granted for centuries, ideas like absolute space and absolute time.
Einstein's logic was actually beautifully simple, but incredibly profound. He basically said, look, if the speed of light is the one thing that is absolute, the one constant for everyone, no matter what, then something else has to give. Something else has to be flexible. And that something else, he argued, was space and time. Your measurement of distance, your experience of time passing, they're not fixed, they're relative. They actually change depending on how you're moving, all to make sure that the speed of light stays the same for everybody. Wild, right?
This idea was the seed that, 10 years later, grew into his absolute masterpiece, the theory of general relativity. And with it, he just completely rewrote our understanding of gravity. He said gravity is not some mysterious force reaching out across space and pulling things together, like Newton thought. No, he said it's much weirder. It's just what we feel when mass and energy actually bend and warp the very fabric of reality, a unified, four-dimensional fabric that he called space-time.
Okay, to get your head around this, think about taking a flight from, say, New York to Madrid. If you look at that flight path on a flat map of the world, it looks like a big, long curve, doesn't it? But if you look at it on a globe, you can see that it's actually the shortest, most direct route. It's the straightest possible path. And there's a name for that path. It's called a geodesic. It's what a straight line looks like on a curved surface. And believe it or not, that is exactly what's happening with the planets. According to Einstein, the Earth isn't being pulled by the sun's gravity. It's more like the sun's enormous mass has created a huge dip, a huge divot in the fabric of space-time. And the Earth? It's just moving along the straightest path it can. It's geodesic, through that warped space. So what we feel is the force of gravity. It's really just the shape, the geometry of the universe.
Now, Einstein's theory of general relativity, it's been tested again and again for over 100 years, and it passes with flying colors every time. It perfectly describes the universe on the huge scale of planets and stars and galaxies. And yet, and this is the amazing part, it's still not the final word. Our picture of the universe is still not complete.
You see, what we've discovered is that there's this massive, fundamental conflict right at the heart of physics today. Our entire understanding of the universe rests on two giant pillars. On one side, you've got general relativity, which gives us this beautiful, smooth, predictable universe of the very large. But on the other side, for the world of the very small, atoms and particles, we have quantum mechanics, and that world is fuzzy, chaotic, and based on probabilities. And here's the kicker. The two theories just don't work together. Mathematically, they're completely incompatible. They can't both be the complete story.
So the biggest, the ultimate quest in physics today is to find one single, complete, unified theory. A theory of quantum gravity that can finally weave these two incredible pictures together. This search for what some people call a theory of everything, it's really just the next step in the same journey that started thousands of years ago, when Aristotle first looked at a ship on the horizon and just dared to ask, what is the real shape of our world? It's a quest that has taken us from turtles, to spheres, to a giant clockwork machine, to curved space-time, and now into a future we have yet to imagine.